one to talk about, apparently, number 6, causing the most difficulty. All right, so in this one, we're generating an equation kind of the same line, but in such a way that some given t value gets a point that we want. So they're kind of doing it a little bit backwards to what you think. So here they say they want r of 0. So what's our vector equation of a line first of all? Let's write that down. So r sub t. So that was like our x, y, z equals. What was our equation of a line? Remember? Our point, yeah, so a point, do we call it like x1? What do we call that? x0? Not? Is that what we did, like that? Yeah, so this is the point we know, right? This is the point we know on the line as a vector, plus every scalar multiple of? No, every scalar multiple of? The direction vector, right? Remember, so we had a vector from the origin to the line, and then we had the parallel vector to the line, or the direction vector to the line, and if we scaled that by any amount, t, that would give us every point on the line when we added those two vectors together. So review that video. So this doesn't become just like formula-based. This really should make sense, why this vector equation makes sense. So that's like this. Okay, and so we call this, so this is a little strange. We haven't seen that before. So this is really like x, y, z. So anytime they have this is just what we said was like every point on the line as a vector, x, y, z. That's what they mean by this r of t. That's every point on the line, what we call just the vector x, y, z. Okay, so we got 2 points on the line, -3, 3, 3, and -1, -7, -8. And so they want us to get specific forms of the line so this is saying when t is 0, when t equals 0, we want our equation of the line to generate what? Point P. And when t equals 8, we want the equation of the line to generate point Q. So let's start with the first. When t equals 0, we want to get point P. So what will that mean for us setting up this equation here? When t equals 0, so imagine t equals 0, we want the result to be point P. So what does that tell us right away? Initial point has to be the point P, right? So that when t is 0, you'll just get -3, 3, 3. That's what this says. When t is 0, we want to get -3, 3, 3. Very good. Okay. Now, the other thing is that when we plug 8 in for t, we want to get the point Q. Remember, any scalar multiple of the direction vector of the line will work. So there's only one that's going to be such that when we plug 8 in for t, this thing's going to give us point Q. That's the one we need to find. Does that make sense? Okay, so we'll just do it. So we say we want, when we plug 8 in, what do we want to get? -1, -7, -8. So where does that go? On the, over here, right? So we want to, when t is 8, we want the equation of the line to give us -1, -7, -8. So then now the A, B, C should be uniquely determined. All we need to do is, well, no, so we have to do it for all three. Right, so what? So we have 8 times A plus -3 equals -1. So now we can make like the parametric form. And we can say -1 equals -3 plus 8A. That's the x coordinate. Okay. And then -7 equals -3 plus 8B. and that's for the y component. And then negative 8 is going to equal negative 3 plus 8c. And that's for a z component of the direction vector. So then those are easy to solve for a, b, and c, and that will determine what a, b, and c are. So what is a? Let's just make sure we're right here. So let's go ahead and put it in. So we want what? Negative 3, comma, negative 3, and negative 3, plus t times. So what do we get for a that makes this true? 1/4. Is that right? 0.25. Add 3, you get 2. So 8 times 1/4 is 2. Okay, what about the next one? You get negative 4. Is it negative a half? And finally, we got negative 5. So what would it be? Negative 5/8. Am I doing the math right? So let's check it. If I put 0 in for t, I should get point p. Do I? Yep. R of 0, they're saying that when t is 0, you should get point p. When r is 8, you should get the point negative 1, negative 7, negative 8. So plugging 8 in here, this would be 8. A quarter of 8 is 2, plus negative 3 is negative 1. That's good. 8 times negative a half, negative 4 plus negative 3 is negative 7. That's good. 8 times negative 5/8, negative 5 is negative 3, negative 8. I think we got it. Correct. Okay, so that gets you started on that one. That's kind of the gist of this. So because there's an infinite number of ways to write a line, they're specifying which way by giving you particular points that you should get for particular t values, and that will determine exactly which version of this same line that you're going to write. So all these are going to be, all your answers are going to be different versions of the line through PQ. Okay, questions on that? Does that help?
This was number 7.
6, I think. 6. Any questions on that? Okay, so the next topic is planes. Planes. So we do lines and then we do planes, but important to note that these are totally different animals. These are apples and oranges. Cats and dogs, okay? Why? So let me sketch a line. So here's like a line in space, right? It's the best line I've drawn all day. So I got this line, and then I got this plane. Why are these like, why would you not put these two kind of mathematical structures in the same category? What's different about them?
Dimensions.
Yeah, what about dimensions?
Plane has 2 dimensions, but a line is 1.
Yeah, so a line just kind of has 1 dimension. So you can go forward and backwards, but that's kind of the same dimension. And so then, how do we see that in the equation for a line? It's just you have the 1 parameter t, right? The 1 parameter t can generate every point on the line. You have 1 variable, 1 dimension. Hey, what about a plane? So it's like when you're on the plane, you kind of have 2 dimensions to go on, right? So these are different, right? They're different. That's what I'm trying to say. So, but in terms of writing the equation of a plane in space, we start with the same premise that we want a point on the plane, and then we want something that determines the orientation of the plane, right? So if we had a point on our line and the parallel vector, the direction vector, that uniquely determined the line, right? So same thing with a plane. We want So we want, if we had a point and something that gave us this particular orientation, then that would uniquely determine the plane as well. So let's talk about the orient. So having a point on the plane, that's easy. So just some point in space, an ordered triple will be a point on the plane. So then what about the orientation? So what kind of thing is going to be able to lock down the orientation of this plane? So what would do that? And so my first question is that a vector in the plane? Does a vector like in or parallel to, that's the same thing, right? Vectors are mobile. If I had a vector parallel to the plane, I could come and set it in the plane and it would be the same vector, right? So a vector like that, parallel to the plane, does that give me a unique orientation of that plane? Daniel, you're shaking your head. Why not?
I guess it would tell you like one angle, but you can still rotate it around the vector.
You could still rotate it around. So I brought my matching yellow paper for our yellow plane. Okay, so here it is. So if this plane is like this, and that vector's in here, does that vector uniquely give me the orientation of that plane? No, because that vector, you could spin it, right? You'd have an infinite number of orientations such that that vector is in the plane. Does that make sense? So a parallel vector does not lock down how this plane is oriented. Okay, other ideas? Yeah.
So then maybe like a vector coming out of the plane or like perpendicular.
A vector perpendicular to the plane. Would that uniquely determine the orientation? So if we're saying here's this vector, and now we want a plane orthogonal to that, does that lock it? Does it lock its orientation if we're perpendicular to that vector? Just orientation now, just how it's kind of angled in space. So you should be thinking yes. If I pick a vector, like this, there's only one kind of inclination or orientation of that plane that's orthogonal to that vector. Make sense? Is there only one plane that's orthogonal to that vector? No, there's many planes, right? But they all have this, you think about a bunch of parallel planes, they all have the same orientation. So that's where the point comes in. So if you have a point and that orientation, now you've locked a particular plane. Does it make sense? Cool. So orientation of a plane. So we really kind of actually have three terms for this. So orientation of a plane is determined by an orthogonal vector. But there's actually two other terms we're going to use that mean the same thing in this case. What's another term besides orthogonal we could say? Perpendicular. And then there's another one. No, yeah.
Normal.
Yeah, so normal. So this term normal is going to have the same meaning for us as orthogonal, normal, or perpendicular. So the orientation of the plane is determined by the orthogonal vector, also known as a perpendicular vector, also known as normal vector. So that vector is normal to the plane. Okay, so how do we use the so what we're going to do is, the first thing we're going to do is, there's our point on the plane, and then I have a vector, just like we did with a line, the point on the plane, we're going to take the equivalent vector in standard position, right? Has the same components as the coordinates of the point. Spin here. Okay, so there's my point. And I'm going to take I'm going to write a vector in standard position that has the same components as the coordinates of that point. We know that that will just then go from the origin to that point. And then I'm going to take my normal vector and I'm going to set its tail on that point. Right? Normal vectors are mobile. I can put that thing anywhere I want. I'm going to come along and I'm going to take my orientation or my normal vector, set its tail right there on the point that we know. Okay, so well, what am I after? I'm after every point on the plane, right? So we have this red vector is like every point on the plane. So the question is, how do we model? That's going to be my XYZ like we had in the line. It's going to be my XYZ. How do we use the given point and the normal vector to come up with this vector that I'm showing that will give us every point on the plane? Does the task make sense? Okay, so this is my known point. Okay, my normal vector. Because it's giving orientation, like the parallel vector gave me orientation of the line, I'm going to use the same thing. But now here you got to be really careful, right? Because what is the vector ABC for a line? How is it related to the line? No, ABC. The direction vector. And how is that direction vector? What's its direction relative to the line? Parallel, right? It's in the direction of the line. It points in the direction. It's parallel. But now the ABC for a plane is in what direction relative to the plane? Perpendicular, orthogonal, normal. So you really got to keep there's lots of problems that involve both. You have a line and a plane. So you have to, if you're using the same symbols ABC, you have to keep it straight. That if that ABC is for a line, it's parallel to the line. It's pointing in the direction of the line. If that ABC is for your plane, that vector is orthogonal to the plane. Okay? And then our red vector here is every point on the plane. So we need a relationship that brings all this together, right? So how can we come up with some kind of relationship that brings all three of these together and then therefore gives us every point on the plane, x, y, z? Any ideas? Yes, sir?
Like find a vector on the plane and take the cross product of that and ABC.
Okay, this is a good thought. So when you say the vector on the plane, what do you mean? So by vector on the plane, can you be more specific?
Just do final minus x minus the initial x.
Okay, yeah. So do you see that he's talking about this vector right here, from here to here, and that vector is a matter of what operation of vectors? I've got them tail to tail, and I want the vector from x naught, y naught, z naught to x, y, z. Isn't that vector subtraction, right? Remember that? So it's what minus what? It's going to be the red one minus the black one, right? So that vector looks like this. And that's violet, purple. Got all my colors going today. All right, so this vector here is what minus what? Sure, we'll do it all at once. Just subtract x minus x naught, y minus y naught, and z minus z naught. That's this one right here. And that vector is parallel to the plane. It's in the plane. right? It extends, its tail is at my known point, and its tip is at every other point in the plane. Every other point in the plane is here. And the tail is at the known point. So now we gotta, what's the relationship between all of those vectors, every single vector that starts at x naught, y naught, z naught, and ends in the plane somewhere? What's the relationship between that vector and our ABC orthogonal vector? What are they? Perpendicular. So mathematically, I've got vectors that are perpendicular. What can I do? Yeah?
Well, we know that the dot product between any two perpendicular vectors is always 0.
Dot product is 0. Is that true? Yeah, so that's our mathematical relationship. We can take every vector in the plane starting from x naught, y naught, z naught. We know that the dot product with that and our perpendicular vector will have to be 0. And that will frame our, so get the blue here, our orthogonal vector. Has to be 0. So that brings it all together, right? That brings together our every point in the plane, our known point in the plane, and our orthogonal vector in a relationship that will always be true for every point in the plane. Yeah?
By solving for the perpendicular vector that is perpendicular to the plane, you find all of the points that are.
We're not solving for any particular thing right now. We just set up a true relationship between all this stuff. So normally you'll know or you'll figure out what the orthogonal vector is, and so knowing a point of orthogonal vector, you'll have. So we're not done yet. So let's just do the math here. So doing the math here would mean what? What would it be? A times x minus x naught. Yep. Equals. So that's our first form of the equation of the plane, because so what's known and what's fixed and varying? A, fixed or varying? Fixed. X, varying. X naught, fixed. And that's the same for all three of these. So your ABC is your known orthogonal vector. You just plug in the ABC. And then x naught, y naught, z naught is the known point. Plug that in. Leave x, y, and z as they are because they represent every point on the plane, the x, y, z. And that's it. So this is, if you're creating the equation of a plane, you want to use this. And what two things do you need to do it? So by initial, you mean any point on the plane and orthogonal vector to the plane. If you have those two things, you just plug them into this and you got your equation of the plane. So that, okay. But we can keep doing some math here. We can keep going. And we get what? AX plus BY plus CZ equals. So this would be minus AX naught. I'm going to bring it over to the other side as positive. Is that okay? And this is minus BY naught. I'm going to bring it over to the other side. Is it okay? And CZ naught. Now, what about these? Any variables here? These are all known values, right? So that thing just is some number. It's just a value. So I can call it D. So now AX plus BY plus CZ equals D. It's another way to write a plane. So if you're asked to write a plane, you're going to use this. But oftentimes in a problem, you'll be given a plane, and it'll be like this. So what can you glean right away from this? Looking at an equation like that, what do you know right away about the plane? Yeah. Yeah, so you know the coefficients form the normal vector ABC. All right? Now, what if you want to know, I mean, by looking at that immediately, do you know a point on the plane? 2x minus 3y plus z equals 5. There's an example of a plane. It's not this yellow one. So, what do you know right away? So just looking at that, you know that the normal vector is 2 minus 3, 1 is a vector orthogonal to the plane. Okay, that's my orientation of the plane, right? It's a normal vector for the plane. Now, how would I generate points? So this isn't just the label or the name of a particular plane. It's mathematically equivalent to the plane. How is this equation mathematically equivalent to a plane like this gold one here? How would they it's a mathematical representation, not just the name of it. Oh, here's a plane. Its name is 2x minus 3y plus z equals 5, right? No, this is mathematically equivalent to some plane in space. So what's the connection there? Can you tell me a point on this plane? Yeah.
Yeah, so any combination of x, y, and z that gives you that 5.
Right.
If you plugged in 2 of those values and then found the third value.
Right. So tell me.
So, like, let's see. So if x was 1 and y was 1 as well,
Uh-huh.
that would be -1 plus z equals 5. And then you can find z is 4. Or no, 6.
See what he did? He set x and y equal to 1. That determines what z has to be to make this equation true. What do we know about the point 116? It's on the plane. It's on the plane. What about 0, 0, 5? Does it make the equation work? Then it's on the plane. What about 10, 100, 3? What do you think? This point does not make this equation true. Therefore, not on the plane. It's a lovely point. It's a nice point. But it's not on this plane. Okay? So find 3 more points on the plane. Go. Just yourself. Find 3 more points that are on the plane. Okay. Tell me. Let's see. Steve, did you find a point on the plane?
227.
227. Does it work? Someone else get that one? All right. Somebody else? Tell me. What's one you found? 103. Does it work? 1. Yeah, works great. Jose, tell me.
203.
203. I don't think 103 and 203 can work. So 203 is going to be 4. It's going to give you 7. It's not going to give you 5.
312.
312. Does it work? 6 minus 3 is 3, plus 2 is 5. Good. Get the gist of it? Any ordered triple that makes that equation true is a point on the plane. That's why this is the equation of that plane. Any ordered triple that does not make that equation true is a point off the plane. That's why this then represents all points on the plane. All points, x, y, z, on the plane. Any questions? Okay, so notice, what did we start with to find the vector, or find the equation of the plane? Lots of vectors, right? And where did we land? The equation, right? No vectors. Okay? So with a line, right? A line was a vector equation of a single parameter t. A plane ended up being an equation of x, y, and z. Totally different, right? Totally different. So the string of points in space ended up being a vector function dependent on one parameter t, and then the plane ended up being an equation of x, y, and z. So that just underscores that they're different. They're very different animals, right? They're very different. Okay, so I have a few extra sheets, but hopefully you brought your sheet from last time. We're going to flip it over and work on the plane side. I got a few extras. But again, like last time, these start really easy, and then as you progress, there's more and more problem solving and thinking and figuring out what you have to do. Work together. Don't go on to the next thing until you're good on the previous. I'm coming to you. Don't worry. How many people need one? So we're going to have to share. I've only got 3 left. The rest of you, sorry, you're going to have to share. Someone next to you. Or I'll put it up on the board. Put it on the screen. I got one more. I'm gonna put them up on the screen though.
So this number equation is like
Okay.
So like, I have to like this. I thought, right? If I do that, you write it as a coefficient, right? So I know this that one. I draw this good. Oh, so you have to do cross product?
Yeah, and then you take the cross product to find the normal vector. You have that. Well, the vector, so like the vector, like right here, just want to put that in its normal vector form, like -1, -3, 2, and cross product it with the vector from this point to that. That's your normal vector.
Okay, I put the answers for 0, 1, and 2. So check your answers for 0, 1, and 2. 0 is just plug in the numbers. So if two planes are parallel, then what about their orthogonal vector? What about their orientation vector? Parallel planes? If parallel planes, then what about their orientation vectors, their ABC vectors? They're the same, right? Or scalar multiple of each other, right? So if you want something parallel to P1, you can use the same normal vector as P1. Does that make sense? If you have two planes that are parallel and you've got the normal vector for one of them, that's also the normal vector for the other. So I just picked off the normal vector 2, -2, 1, and used the new point. And that's the equation of the plane. Question?
So I noticed in both your equations, you have x minus 1 and x plus 1.
Yep.
Are they supposed to be y's
Oh yeah.
or? Okay.
Did I do that twice?
Yeah.
I'm
That's
not-
why I was confused. I was like, I guess he's doubling down.
I'm not very good at math. It's crazy, right? Is that better?
Yeah.
Yeah, thank you. Sorry. Okay, how about 0 and 1? Are we good? What about number 2? So if I want the equation of the line normal to the plane, then what can you say about the vector 2, negative 2, 1 for that line? It's the direction of the line. It's the direction of the line, right? Because if you have a vector that's parallel to a plane like my hand, then that'll be the direction vector for the line. So I just pulled it off. So now my direction or my parallel vector for the line is just the 2, negative 2, 1. Does that make sense? So then I just use that and then the point I was given and use my equation of the line. Questions on 0 through 2. So now I've set up some pictures for 3 and 4. L1 and L2 are not parallel. We can see that by the coefficients here. The direction vectors of L1 and L2, they're not parallel. So if there is a plane, which I'm assuming there is, then these got to be intersecting lines. These have to be intersecting lines. If they're skew, there'd be no plane. So they're intersecting lines, and so it's going to be the plane containing those two intersecting lines. So what do we need? We need a point in the plane. Do we have a point in the plane? We got two of them, right? Because if it's a point on the line, then it's a point in the plane. Okay, so either of these 2 points will work, or any point on L1 or any point on L2. Those are all valid points that we could use for the plane. The question is now, how do we get the normal vector? How am I going to get the normal vector for my plane so I can write the equation of the plane? Yeah, Daniel. Well, that works. So if I have this parallel vector to this line and the parallel vector to this line, which are both parallel to the plane, and I take the cross product, I get a vector orthogonal to both, right? I get a vector orthogonal to both those vectors and therefore orthogonal to that plane. Right, so you can do the cross product of your two direction vectors. That'll give you that black vector that I've drawn. And then use any point that you want on either line. And you can set up the equation. All right, last thing to talk about here. Number 4. So now I need the equation of this plane. I'm half done because they flat out gave me a point. So again, how am I going to get the orthogonal vector to the plane given a line and a point? Any ideas? So again, if you ever have two different vectors that are parallel to the plane, you can take the cross product. So can I get that? Can I get two vectors parallel to the plane? Ellie, tell me.
Use the initial point for L2
Okay.
and create a vector with that extra point.
Right, so my initial point is 519. I've got 519 here. I can create a vector from 519 to 132, right? Do I have another vector parallel to the plane?
L2
What about L2?
is a line parallel.
But I need a vector parallel. So what's...
Direction vector.
Yeah, so I can use the direction vector for L2. -1, -3, 2. I just found two vectors parallel to my plane. The direction vector of the line and a new vector that I made from the point on the line to the other point on the plane. Cross product, boom, got it. Normal vector. Do you follow? Cool, so maybe we'll do the same thing as last time. But I'll just draw pictures. We won't do the math. We won't do the actual numbers. We'll just talk. So what do I need to write the equation of a line? So this is to write the equation of a line, right? So, and that's the intersection of those two planes. So what do I need to write the equation? Just in general, what do I need? Point and direction vector, right? Okay, so how am I going to get let's start with the point. So instead of, does anybody have planes P1 and P2 and you're pretty confident on the equations? Do you have them yet? P1 we should have. What's P1?
Negative 2x plus 2y
Negative 2x plus
minus z equals negative 4.
2y plus z
Minus z
minus z equals
equals negative 4.
-4. Are we good? All right, and then anyone get P2? Anyone get that far?
I might have it, but not as confident as.
Let's just write down what you have, and if it's wrong, then we'll just find the line that's the intersection of those two.
Okay.
That's fine.
Negative 11x plus 13y plus 13 plus 14z equals 84.
Equals 84?
Yeah.
Wow. That's a serious plane right there. Let's see. So let's just, if we check these two points, 1, 3, 4. So negative 11, 39, and 56. All right. Seems about right. Then negative 55 and 13 and, oh geez, forget it. Okay, so we're just gonna go with that. All right, so how are we gonna get a point on our line? So if it's on the line, then what's also true about it in this scenario? Right, it's gotta be on both planes. So we need a point, any point that satisfies both equations. How can we get that?
You just make a system of equations for.
Right, but we have 2 equations and 3 variables. So that makes it a little easier. Because what we can do is we can just let, say, z be 0. Get rid of this 14. This 14's our biggest number. So if we could let z be 0, and then we'd have, I'll divide by 2. Minus x plus y equals negative 2. Is that right? Divide by 2, divide by 2, divide by 2, yep. And negative 11x plus 13y equals 84. And if I solve those 2 equations, I'll get my x and y coordinates that go with z equals 0, and that'll be a point on the line. Good? All right, half done, right? Got the point. So now, how about the direction vector of this line? So, how am I going to get a vector that's parallel to that line from these planes?
You solve for another point on the line.
Oh yeah, that would work. That's a good idea. So you'd have to do this procedure again. You can do this procedure again and get a second point, and then you could get the direction vector of the line. That's one way. Okay, that's good. How about something a little more novel than that? So no, that's totally valid. That will work. But in terms of the geometry here, is there another way, geometry-wise, rather than more algebra-based, that we can get that vector? So what do we know about these planes, right? What do we know? We've got I got a perpendicular vector that way, right? That's normal to this plane. Colors are fun, okay. And then this vector is perpendicular to that plane back there. Would that work? See that? Yeah, so if this blue vector is if this is say L1, then this is my 4, negative 2, 5. And this is, say this is L2 back here, this one. And this is my negative 1, negative 3, 2. This is my L1 orthogonal vector, 4, negative 2, 5. So, would the cross product of those two vectors give me a vector parallel to the line? Yes, because both of those vectors are orthogonal to the line, right? The line lies in both planes. So since the line lies in both planes, each of those orthogonal vectors are orthogonal to that line. So a cross product of those two would be orthogonal to both vectors and therefore in the direction of the line. So yeah, cross product of the normal vectors gives the direction of the line, and then you could use the equations of the planes to figure out a point on the line.